Okay. Let us review first actually what should be talked today and why it should be talked. Okay. Let us first begin with why it should be talked, because many of you know that aromatic chemistry begins with electrophilic substitution reactions, and very occasionally these nucleophilic substitution reactions are taught. The origins are quite obvious. Those are the classical reactions well established. The profile of the aromatics under the electrophilic conditions are well standardized. So, one can quickly predict what should be the product, what should not be the products. Okay. But there are some inherent problems. Inherent problems means these problems of isomerism. So, that means the formation of different kinds of isomers are produced, all of us know, and traditionally when it is taught, it is given the idea that the electrophilic substitution reactions produce orthopara mota for monosubstituted benzene rings. Okay. So, in case of heterocyclic, the situation even more acute, simply because if you think about nitrogen, let us say pyridine, how many pyridine monosubstituted, let us say pyridine itself is having what 1, 2, 3 different kinds of. Then if you have a monosubstituted pyridine, you will have 4 different chemically non-equivalent hydrogens. So, you have, that means the problems are severe. Then if you go to naphthalene, for example, monosubstituted naphthalene, think about monosubstituted naphthalene, how many chemically non-equivalent CH bonds are there in naphthalene, monosubstituted naphthalene I said. How many? CH, nuclear CH bonds. No. See, that is the reason. You have to look into the problem very carefully. Let us say, okay, let me write. When I talk about monosubstituted naphthalene, how many nuclear CH bonds are there which are chemically non-equivalent? 7. So, that's, so you see, that means these things are little tough, that means the problems are more acute. But and if you recall, in the last year we talked about the selectivity. Selectivity is one of the first and foremost goals in the organic synthesis. And if you recall again, just go back to the last class, Minsky reactions. Minsky reactions on quinine, it specifically functionalizes the 2 positions. You have so many functional groups around the molecules and so many double bonds around, but specifically one position is functionalized. So, that is called really selective reactions. So, like many of you probably know that the click reaction, for example, click reaction is so selective towards the triple bond. That means, whatever the molecules have in their structures, but eventually the reaction will take place only in the triple bond and with an azide. So, selectivity is a very important goal, and that means and then that is one of the major reasons why we will be talking about that lithiation today. Why lithiation? We have studied organomagnesium, right, from our very early stages of studies of organic chemistry, but lithium, organolithium has a special characteristics. One of the special characteristics is that selectivity. You can achieve selectivity with organolithium compounds, and that concept has been extended to heterocycles. Okay. So, today what do you do? We will just very briefly, because some of you have studied my organic synthetic chemistry course. So, we have talked about quite a bit of organolithium chemistry there, and but some of you have probably do not have not studied. So, what we will do today, just very roughly we will review what is organolithium, what are these reasons why organolithium compounds are superior to organomagnesium. Okay, some of the typical reactions, and then switch over to the applications in heterocyclic compounds. Okay. And today again all the discussion should be limited to the 5-membered ring systems. 5-membered ring system means furan, pyrrole, thiophene. This is the order we will be talking about, because organolithiums are more useful in furan chemistry, and followed by thiophene and pyrrole chemistry, and maybe little bit of these lithiation in indole chemistry. So, we will talk about those reactivity patterns, and then towards the end of the class, if the time permits, we will talk about the applications of these. Okay. And so, when we talk about these organolithiums, I think by now all of us know, right. And so, what do you do? How to make it first, and what is the master reagent? If you recall, butyl lithium is the master reagent. How do you make it? Butyl chloride and lithium. So, N exchange. So, that is it. So, that means sort of a reductive kind of thing. That means and then lithium chloride, etc. Okay. So, this is the master reagent, butyl lithium, alkyl lithiums, and reason is quite obvious, that is the most basic organolithium compounds, and there are other methods. There are only, if you try to classify the preparations of organolithium compounds, there are only very few. If you begin with a master reagent like alkyl lithium, first the type of the preparation could be deprotonation, just abstract the proton, that is one of these reasons why. Then second mode of preparation, I would say, or else you can say first mode of preparation, halogen exchange. If you have an halogen and alkyl lithium, you get an exchange of these lithium and halogen. So, that is how, but the driving force is almost always the thermodynamics. That means, the lithium organolithium that will be produced would be lesser acidic, lesser basic than the parent. Like when I talk about this, that means let us say you have butyl lithium, for example, then and take bromobenzene. So, what you would like to see? You would like to see that phenyl lithium is produced and butyl bromide is produced. Why? The driving force here, because these phenyl lithium is less basic. So, that is basically the idea. So, so we can have this, and what else? What I said, then the other important point about the organolithiums, they are always more reactive than corresponding organomagnesium compounds. That is you have to remember. That means, let us say you have for example, this is something you ought to know. Let us say you have a reaction with butyl lithium and butyl magnesium bromide. So, what difference do you expect out of this reaction? So, that when I talk about the organolithiums, actually we always talk about their chemistry with reference to the organomagnesium compounds. The reason being, all of us know that they are well studied. We know a lot about organomagnesium compounds. So, the mechanism, the activity profiles, etc., etc. And if you study organolithiums with respect to organomagnesium, that would be easier. In this case, for example, if you what difference do you expect with respect to the product formations? I think very similar product, right? Very similar product. If you have excess, what you will get? You will get the corresponding tertiary alcohol, right? So, similarly, if you have excess, here you will get the same product, but what you will see, there is a remarkable difference in the reactivity. Maybe at minus 78 degree, Grignard would not react, but the corresponding organolithium would react very nicely, very nicely. That means, by controlling the temperature, you can actually achieve the selectivity. That means, at low temperature, maybe you can stop the reaction of this butyl lithium at the ketone stage. There are examples also, and also there is another. So, that means, in nutshell, that organolithiums are much more reactive than the corresponding Grignard, number one. Number 2 point, organolithium compounds will have a tendency to undergo chelations and coordinations. That gives some of the intermediates very high stability. Okay. I think I taught all these things in the 4th year, if you recall, right. How to straight away get to the, this is a typical JEE question or GATE questions or whatever, I think all of you know, right. No. Very good. So, what is the secret? Secret is that after the addition of 1 equivalent of methyl lithium, the intermediate becomes stable because of the internal coordinations or the chelation, you can say. So, these are the properties that actually that make the difference in the reactivity. Okay. And many of you probably know, I do not know whether just whether I should talk about. Okay, let me talk about this. This is again a question of the effect of the heteroatoms, for example. This one, amide normally do not react. Amides normally do not react with organomagnesium compounds, because their organomagnesiums are less reactive. But if you put, let us say, sec-butyl lithium, fine, that means you get a different kind of the reactivity. If you compare this one, absolutely there is no reaction, fine. So, so this is the tip, this is what something I mean remarkable in the sense, in the benzene chemistry you will be getting only single product. That means lithiation takes place here at the ortho position, and there is no question of these isomeric formation of the isomers. That is the beauty of the organolithium compounds. Okay. And that too, you see that functionalization can be done ortho to an electron withdrawing substituent, apparently electron withdrawing substituent. But what is the requirement? Requirement the presence of an heteroatom. So, heteroatom is very important in aromatic chemistry and lithiation, and that we will see that in the, okay. Then there the effect of the heteroatoms in the heterocyclic chemistry also would be observed. Now, look at this one. Butyl lithium. So, N-butyl lithium. So, what do you expect? So, the reaction that takes place here is, yes, somewhat correct, and actually what you will get? You will get this, simply because it is very nucleophilic compared to the Grignard, it will undergo that. But what you will find, it stops there. In case of ester, you had the over addition and straightway went to the tertiary alcohol, but in this case this reaction stops here because of the again coordinations. So, these are the properties basically, that is what I have to, it is very reactive, it can be controlled because of the coordinations, etc., and so, and also the third point that has to be noted, that organolithiums have tendency to be soluble in organic solvents. Okay. So, and of course, I think many of you probably know who is the father of organolithium compounds. You have to know a little bit of history also. History, Gilman, Henry Gilman. But what you people do not know, George Wittig also was the inventor of organolithium compounds, and there is actually a rearrangement called Wittig rearrangement. I do not know whether you know or not. Wittig rearrangement. It is a 2,3 sigma-tropic shift, 2,3 sigma-tropic rearrangements. So, that means George Wittig, I mean, is not only known for his Wittig reactions, also it is known for this. Okay. And so, I think we have sufficiently talked about the background. Let us look at a little difference actually. Let us see. There are several tricky differences. Maybe we can talk about. I think I will just give you one example that will okay. So, from the aromatic chemistry, what you will find, if you have a substrate, differentially functional substrate, with in one case you have a nitrogen, in other case you have methoxy here, you see there is also a diversity in the reactivity pattern. So, this is basically an example of that under very similar conditions, but with little difference you can have a different kinds of the reactivity. Okay. Let us say if you react this with butyl lithium, just when I write butyl lithium, basically it meant to be N-butyl lithium, okay. And the solvent is very critical, that is what this example is about, solvent hexane. In one other case, if you have let us say butyl lithium and Timeda, many of you know tetramethyl ethylene diamine and ether and hexane also little bit. So, there is a remarkable difference. So, what do you expect? In the earlier example, you have seen that if you have a functional group containing a heteroatom, it can induce ortholithiation, and if the lithiated agent is not a bulky one, then it can straightaway react with the carbonyl group. So, it has to be tertiary butyl lithium or secondary butyl. In most cases, ortholithiations are done with secondary and tertiary. Okay. Now, here is a case that what you see that the conditional difference, that is I mean the reaction conditions, effect of reaction conditions, that would also tell you something about the factors which actually dictate the positions of the lithiations or the reactivity of the lithiation. Let us say there are two. So, when I say butyl lithium and hexane, what does it mean? You have to have a little meaning of it. That means butyl lithium itself structurally like a cuban kind of structure, many of you know. Tetramer, right. So, so that means they are supposed to be an aggregates of the 4 units. But when you add Timeda actually it breaks up, it breaks the tetramer. So, that means it is free. So, it becomes more basic. That means it makes it non-coordinating. The system is non-coordinating, that means it cannot form chelation etc. all these things. That means it will be guided by the acidity and basicity. Now, I think all of us can guess which one in this case, which one is acidic and which one is basic. Okay, okay. Let us say let us begin with the first one. Let us say first one, what I said is a non-coordinating. That means if the lithiation takes place alpha to this one or this one, then there is a propensity to undergo coordinations. Now, if you look at this, if you lithium here and lithium here, which one would be having a better coordination? No, nitrogen or oxygen? Nitrogen, obvious. So, that means under the non-coordinating conditions, so the lithiation there to take place is this one, because nitrogen is more basic and the solvent is not undergoing any coordination. So, intermolecularly, so this is a chance. Okay. And the other case, obviously the other case the coordination, that means there is a diversity. Basically what I am trying to say, if you just keep on changing trying different solvent system, and what you will find in this case, and apparently well, it is very difficult to say, apparently this is actually due to this acidic, that because oxygen is more electronegative, is adjacent to it, and there is a possibility, and of course the coordination is there, but this may not be undergoing intramolecular coordinations. It is primarily due to the higher acidity of this hydrogen adjacent to this oxygen could be the driving force. I mean, sometimes these arguments are not really acceptable, but I mean it is a useful working guideline. Okay, then acidity. So, that means lithiations are dictated by two important things. What is that? This acidity and the coordinations. So, these are the two, okay, acidity and the coordinations, and there are okay, there are other examples. Maybe sometimes also you have to talk about the repulsion between the anions and the lone pairs. Okay, let us now straight away come to these 5-membered heterocycle. I think I will begin with imidazole. It is an N protected imidazole, and you have let us R Now, what you can see, you have 3 different chemical non-equivalent hydrogens are there. Now, if you use butyl lithium, what is expected? So many things is expected actually. When I mean for any reaction, your starting point should be the reagent. So, you have to first have idea about the reagent. What are the different reactivity profiles of the reagent, etc. Okay, that you have to identify. So, we know as soon as you see butyl lithium, we can recognize it has 2 properties, acidic properties and nucleophilic properties. Fine. Now, between the 2 you have to choose one of them. So, often we go for the acidic properties or basic properties, because that is the faster reactions normally. Proton abstracting reactions are faster reactions. So, that is one of the reasons. Second, obviously, you have to take care that addition to the electrophiles. So, these are the things you have to take care, and when you talk about the abstraction of the proton, now we have 3 different kinds of the proton. So, which one is, and how do you know which one is more acidic, most acidic among the 3? So, if I recognize let us say number this is 1, sorry, this is let us say 2, and this is 3, this is 4, and this is 5. 2. But what is the reason? Oh, good. So, very simple then. So, that means if you have an electron negative atom and it is flanked by 2 nitrogen atoms, so it is likely, and in fact, the answer is yes. So, that means you can quickly actually predict the site of the lithiation, and the lithiation takes place here. Let us look at one more example, where you have a different kind of substrates, where you have this is now you have a well defined protecting group CH2OET. Now, once again the reaction conditions are same, butyl lithium. So, what do we expect? We would okay. So, that means again this is 2 and 4 and 5, and what is the region you said is 4 position?
Lone pair negative charge repulsion, I think, because there is bromine.
No, at both adjacent to both bromines there is no nitrogen lone pair actually. If you draw, nitrogen is there close to each other. Once again actually the reaction takes place on the 2 position. So, that means stability, the corresponding conjugate base. So, I mean although the process is different, this is that means the basic guideline is that it is the acidity that would drive the reactions to a specific positions. So, all these things. Now, let me give you one more example, let us say one more example, but it is from a 6-membered heterocycle. You have nitrogen, this is oxygen, okay, benz oxygen, and ester group here. This case not butyl lithium is LDA. LDA is okay, you have to know little bit about the difference between the butyl lithium and LDA. What is the difference? LDA is bulky, non-nucleophilic. It can, because of this bulkiness, actually the nucleophilicity is reduced, that you have to remember, and also acidity wise also it is basicity wise less basic than butyl lithium. You can guess, because the P corresponding anion is more stable for the LDA. Okay. Now what do you expect out here? So, LDA, that means not nucleophilic, that means it will not react with the carbamate carbonyl. So, that means it should undergo, it should actually promote deprotonation, right, and there is no halogen in this case, deprotonation. There are what you can see, so many hydrogens here, you have perihydrogens here, perihydrogens, and all these things, these hydrogens. I mean, if you recall the carbanion chemistry, in carbanion chemistry you do not see often a vinylic carbanion, never, but that is the beauty of the organolithium compounds. You can produce vinyl carbanion. Now, you have option now adjacent to oxygen and nitrogen, and which one is, and again the more electronegative atom, which one? Oxygen. That is what yes, but unfortunately the answer is not that. In this case little complications. It is because of the ester group, right. So, why that means the lithiation takes place here, is nitrogen. Now, if you have lithium here, this is so at the same time, not that means what I am trying to say, you have to have a composite kind of factors, acidity, chelation, all the reaction conditions, all these things are to be taken together, then evaluate. Okay, evaluate. So, what you will get is get the lithiation done here. Now, come to the real life examples. The furan, this is a very typical. Let us say if you want to do a furan chemistry, how would you do this? Furan chemistry, all of us know furan is considered to be aromatic, partly it behaves like a diene system, and also partly behaves like more precisely like a phenol. Reactivity is so good. So, many of you know the phenol Friedel alkylations of phenols are not very standard good reactions, simply because of the coordinates of the oxygens with the aluminum chlorides, etc., etc. So, if you want to, let us say, produce alpha alkylated phenol, is it tough? Let us say phenol plus formaldehyde, all of us know. What is the reagent required? Nothing, just mix them, it will form a polymer, phenyl formaldehyde polymer, etc. Cross this, all this phenyl formaldehyde polymer, base, acid, anything. That means you do not need any aluminum chloride or anything like that. This is a process of alkylation or acylation. Okay. So, that is so reactive, that means it is difficult to control. Exactly in case of the furan also, although if you go to the books, they will say suggest okay, such things can be done by alkylations of Friedel alkylation, etc. But very rarely people do it. The yields are not that good, and the reactivity is so high, it is difficult to control. Often you get the polyalkylated furans. So, again organolithium. Organolithium, although it is reactive, but you can just control the reactivity. You just treat this with butyl lithium and you get a monolithiated furan, and what is it? Right, actually what you will find, the lithiation takes place here at the 2 position. Once again, this because of the oxygen, that hydrogen is highly acidic, and one can of course this chelation is something, one can just extrapolate the chelation also a little bit, maybe this oxygen lone pair can assist the chelations, that is a possibility. What next? Then Rx, so you get to this product, but think of a reaction, for example, would you expect a reaction? Less reactive than organolithiums, and most cases, I mean in this case I do not know exactly, most cases if you let us say are MgX and let us say X, then this sort of reactions are very poor reactions, right. We have told you in the 4th year class, that is the one of the I mean serious drawbacks with organomagnesium compounds, and that is the reason why one Japanese scientist has become famous. I mean for all these reactions, coupling reactions, etc. Who is the Japanese guy? Kumada coupling. What is Kumada coupling? Kumada coupling is something like this, only thing that you have to add this Not really, not really. Iron, Fe acid, and there are nowadays there are plenty of. If you just go by another scientist who has also done extensively on this Kumada coupling is known as Nakamura, Aichi Nakamura, okay, E Nakamura. Okay, so I mean then his student also has been working on that also. If you go to the very recent papers in Orglade, they have done something. I don't at the moment I cannot recall, but it's something like this sort of coupling, sp3 coupling in the presence of iron. I don't recall this. Okay. So, in any case, that means what I am trying to say, organolithiums are useful, and in this case you see just monolithiation only taking place. Lithiation takes place only gives you monolithiated compound, and that can be used for various purposes. We will give you more examples later on. Similarly, if you have, you just have to keep also, you have to be a little cautious about it. For example, if you have now, it is a separate situation now, bromo compound and butyl lithium. No, there are two possibilities, deprotonation and butyl lithium and halogen exchange. Now we have to know which one is faster. Normally, when we talk about this sort of carbon ion chemistry, often we said the proton is such a tiny atom, the deprotonation is one of the fastest reactions, especially in inorganic chemistry, acid based titration, the fastest possible reaction, zero activation energy. But when it comes to this deprotonation here, I mean you have a factor, I mean so many, you have actually so many factors to take care. But deprotonation and halogen exchange equally compete with each other. What is meant by that means, I mean the two possibilities could be 50-50, I mean either the deprotonation and these, but from my experience I will tell, if it is a bromo one, then sometimes halogen exchange is much faster. Halogen exchange is much, if sterically free, and if it is a bromine, then actually halogen exchange is faster than the deprotonation, especially in heterocyclic chemistry. Okay. So, this will tell you something then, sorry, this is lithium. What next? If you, this is normally done, all of us know this is normally done at minus 78 degrees centigrade. If you increase the temperature, if you increase the temperature above minus 40 degrees centigrade, you get another reaction done. What is it? Thermodynamically more stable product. Thermodynamically more stable product means 2 lithiated product, 2 lithiated product. So, that is what you have to keep it in mind. Okay. That means, there are possibilities of the rearrangements also after the initial. Okay. So, now we will have one more example. In this case, you use Schlosser's base. I do not know whether you recall or not. Let us see how much you recall. Anybody know or remember? Sorry. So, Schlosser's SCH, something like that. I forgot. Schlosser's base. Okay, we will come to that later. But we are more interested in chemistry. Schlosser's SCH Schlosser's SSER, I guess. Okay, Schlosser's base. Just to check the Google and see what it is. What else? We talked about it in right, potassium T butoxide. Potassium T, that means it is a sort of an aggregate free. Butyl is somewhat more free. Okay, and then also often it is in combination with Timeda, and if you use excess, what you will find? You will find a reaction. That means this is that means dipotassium salt. So, basically you are getting a dianion kind of thing, and obviously the corresponding reactions are corresponding reaction. Let us see, if you have excess amount of the DMF, what is the product? DMF is nothing but is a formulating agent. So, what you will get? You will get actually 2 CHO groups. Why so important? That means, there are very few electrophilic substitution reactions where you can simultaneously introduce 2 other than nitration etc., and harsh conditions you can introduce 2 electron withdrawing groups. Okay. So, this is how one can do. Okay. Then there are reactions also, very, I mean, what you see here, there are specifically 2 and 5 positions, 3 or 4 are unreacted. And similarly, let us say if you have say functionalized furan now, and you can make use of this functional group to direct the lithiations either on this left hand side, when it is 4 positions, sorry 1, 2, 3, 4 positions, or 2 positions. How? That means, you have to make it in the directing groups, and temporarily, this is temporarily you can do it. This is like say again a lithium reagent, is very similar to the EDTA. Any problem? Oh, you cannot see? Oh, what happened? Oh, okay, now, okay, good. So, now we see again a lithiated ligand. So, what do you expect? The expectation is you have a lithiating agent, and so it is sufficiently basic or nucleophilic, whichever, but what is that from the result it has been suggested this nitrogen, this is nitrogen, and then you have 2 carbon, and then again a nitrogen here, this methyl group, and this is a methyl group, right. So, this is methyl group. So, it undergoes nucleophilic addition. This is like if you take morpholine anion, nitrogen anion, okay, that also undergoes addition to the carbonyl group. So, it forms this sort of a geminal oxygen nitrogen compound or intermediate. What next? So, with this presence of this nitrogen ligand here, the lithiation either can take place on this side or on this side, and all of us know this hydrogen, the 2 position hydrogen at 2 position is more acidic, and the lithiation would take place and nicely undergoes coordinations. So, the reagent that means the lithiation that would be the result is again CH nitrogen N, and then 2 hydrogen this, and so you have now a sort of a intramolecularly coordinated, or you can say chelated sort of lithium, and then if you trap this with methyl iodide, the reaction that will be getting is the methylated product and the aldehyde. So, that is it. That means, in situ you are producing a directing group, and during the workup the reaction this directing group is being knocked off from the system. So, that means, you do not really actually you are doing use of, or rather making use of the protecting groups. Instead, it is a temporary sort of a protecting group in the reaction. That means, the whole operation from this aldehyde to this one is a single step reaction. Okay. And there are likewise there are other examples, maybe if the time permits we will come let us say similar reactions are known in the literature. Okay, well, I will come back with examples. Then another directing groups in case of the furan, for example, is a carboxylic acid, and this is also true for other systems. Carboxylic acid, let us say. This is a case now is butyl lithium. If you do a butyl lithium, add butyl lithium, of course, minimum 2 equivalents. So, minimum 2 equivalents. Now, you have all kinds of possibilities, Butyl lithium can nucleophilically attack the carboxyl group, it can deprotonate this hydrogen, and so many things can happen. But with few examples, you can just make a guess. For example, if you recall, conversion of carboxylic acid to the methyl ketone is done by methyl lithium. When it comes to butyl lithium, nobody talks about it. Why? That means the butyl lithium is sufficiently sterically hindered to undergo nucleophilic addition to the corresponding carboxylate salt. So, if you know that, then you can predict what is going to happen. So, the first thing that would happen is that the carboxylic, that means this one would be sufficiently stable, it would not react with butyl lithium, it will not react with, that means butyl lithium will not undergo any addition to this carbonyl group. Now, there is a question, which hydrogen would be deprotonated? There is a hydrogen alpha to this oxygen and there is this one, and 1, 2, 3. So 3. Why? Chelation effect. Chelation effect, that means, so these are the thing actually. How do I know the chelation effect? How do I know that chelation effect win over the acidity effect? How do I know? Okay, your answer is correct. Okay, if just the clue or the key word is that carboxylic acids in heterocyclic chemistry is a directing group. If you remember this, then you should be able to safely predict the location of the lithiation. Okay. So, carboxylic acid group in many cases are the nice directing groups, even in aromatic chemistry also. So, obviously, the next step would be this lithiation here and the carboxylic acid. Okay. And so, we have given you, let us similarly, if you just take an example, a very similar example kind of thing. So, you have NH and BOC now. The conditions again butyl lithium and Timeda. So, what do you expect? So, what is the expectation? That means, when I say what is the expectation, you have to find out the position 2 or 3 and which one. So, that means once again NH is more powerful actually, NH, amide, tertiary amide, they are more powerful directing groups. Actually, there is a review article by Snikas, Victor Snikas, if you are interested. There is a nice order of, they have presented all these directing groups in nice orders, and then from there you can find out which one is more strongly directing, which are moderately directing, which are weakly directing, all these things. So, this is anionic, sometimes we call anionic aromatic chemistry, sometimes orthometallation, sometimes, I mean, there are different names. Okay. So, you can actually from there you can predict actually which one is the strongest possible directing group between, let us say, methoxy and the amide. Amide apparently electron withdrawing, but yet more rather stronger directing group than the corresponding methoxy groups. Okay. And so, in this case it is an amide group, and the product obviously it is product is now is a directed lithiation. That means, the NH is directing the lithiation, not the acidity of this. Okay. And in this example, what been done, it has been reacted with an isocyanate, tertiary butyl isocyanate, because it is pretty reactive. It is, and also it can give the corresponding amide, and most of this sort of amides, many of you know, they are used as agrochemicals. Let me, okay. So, what you see here, in most cases we have been basically functionalizing the furan at the 2 position. If it is in the 2 position, then it is a 3 position. Now, this is an example where, and you can do a lithiation at 3 position. The next example, okay, see here is a furan, now O TBS, butyl lithium and HMPA, hexamethyl phosphoramide. What is expected out of it? Again, you see, there are basically 3 different positions which are equally probable. These 2, 4 and 5, right. 2 important factors, chelation factor and the acidity factor. Acidity factor. If it is a strongly directing group, obviously like amide is a strongly directing group. So, we can just the middle one, we can without any fail we can write that 2 lithiation. But in this case, whether it is an acidity driven reactions or the chelation driven reactions. Okay. It is the acidity driven reactions as well as thermodynamic kind of. Okay. Acidity, okay, that means both acidity and chelation. How is that? If both acidity and chelation, then which one is the position? 2 position, 2 position, fine. But what you will find here, the reaction gives you this is OH and here is the silicon. This is the silicon. That means what is the name of the reaction, Anindya? It is a name reaction. And I thought all of you know. Right. Brooks, not Brook. Brooks reagent. What is it? Brooks reagent is basically transfer of silicon from oxygen to neighboring carbon. No, carbon. It has to be the end, that means thermodynamically more stable. Thermodynamically more stable carbon analog. So, this is now. Now, what next? If you again use excess butyl lithium and butyl tin chloride. Now, you can guess what would be the reaction. What would be the reaction? The lithiation would take place at, there is no other option, 3 position. That is it. That means you can direct the lithiations at your will depending on the situation. That means silicon can be removed at removed very easily from this, and so eventually, and let us say the next okay. I mean the product what we will be getting is the silicon here, the CH2 here and tin here. So, we will have all kinds of that means functionalizations and side by side by the way. So, 1, 2, 3 that means in aromatic chemistry if you want to prepare a 1, 2, 3 substituted aromatics, it is quite difficult. So, these are all these difficult problems can be solved by this lithiation chemistry. Let us look at an example and little exercise on the heterocyclic chemistry. This is a pretty big structure here. You do not have to worry about the structures, just look at the features of the structural features here. So, what are the features basically you look at? So, if you are to convert this into this, it is a very similar molecule. You may or may not write the structure, but only the look at the concentrate on the features. What you will have? What are the features? It is a bicyclic compound. You have an isolated olefin, and also you have an endocyclic olefin. This hydrogen. These are all these methyl groups here and there. So, that means it is okay. And the important structural features here is now you will see a kind of a lactone. That is it. So, kind of a lactone. So, what do you do? That means you have to fill in the blanks. Okay. The blank is basically blank is so 2 steps. So, you do one step here and one more step, it will give straight away this product. So, you have to identify the missing reagents from this. That means you can okay. That means you have to compare the starting metal and the product. Now, if you look at, that means you have to have a 4 carbon synthon, 4 carbon synthon, that is it. What else? 4 carbon synthon means right. So, 4 carbon synthon means very obvious choice is what? Succinic acid, fine, succinic acid. Okay. Any other 4 carbon? Dimethyl malate, any other. But I mean, that means the synthesis itself is very tough, unless then you have to know a little bit of this lot of organic chemistry. For example, actually I will give you the answer. The answer is that you begin with this one, furan. We have been talking about this. Then bromofuran, butyl lithium. I think now we know what is going to happen. Actually, this is equivalent to 3 lithofuran. I think if you are not well versed with the furan chemistry, you will see most of the natural products, most of the, this is also a natural product, this is also a natural product, and this is also natural products named as idiolite, this idiolite. Olite means all of us know, right? Olas means it's macrolites. Okay, actually it goes to this. So, most of the natural products containing furan molecules are 3 substituted, most of them, and there is an obvious reason, of course. If you look at the isoprenoids, and if you convert this isoprenoid into corresponding furan, automatically the substituents becomes the 3 substituents. Okay. So, that is a separate issue, but in any case, and 3 substituted furans in literature also is very expensive. Furic acid, 2 furic acid, these are all very, if you want to make a 3 furic acid, it is not that easy though. You have studied in BSc, right? What is that? Who knows? 3 furic acid, how do you make? Occasionally I teach though in organic synthesis. No. Then means you have to make a 3 bromo. How do you get 3 bromo? Very expensive. Only it is available in Jekaraj lab. Okay, so expensive. It starts from furan. It starts furan plus dimethyl acetylene dead, acetylene dicarboxylic acid, Diels-Alder reaction. I think some of you know now remember. Then partial hydrogenation, retro-Diels-Alder reactions. That is not all. You get 3-4 dicarboxylic esters. You have to reduce the hydrolyze it. Then if you heat it, selectively one of them would go off. Okay. See, that means you have so many steps. Such a small molecule has to be made via a multi-step sequence. Okay. So, it is quite expensive. In any case, but if you do so, what you will find the product that would be forming here, this is CH, of course, just like typical kind of this Grignard reactions. So, what is this one? That is it. That is it. What next? One step. One step. Well, you will get some mixture, but this one step you will get this product. I have taught this. What is this? Triplet oxygen is sensitive, plenty of oxygen, nothing is happening. We are all organic molecules, they are all organic molecules, skin, this thing, that thing, everything is organic molecule, nothing is happening. You have to have a photosensitizer. And what is the photosensitizer? Good, at least you know now, rose Bengal, because it is associated with Bengal. So, you must know this. Okay. It is a fluorescent dye, it is nice, pretty easy. And the reaction is very, I mean, if it works, it is nice. Okay. I think let us, I think I will skip one of the examples, rather I will give you a puzzle. I will give you a puzzle for the next class and see whether you can you try at home. If you fail, I will give you the answer later. And so, this is a kind of a molecule looking like morphine, morphine. You know, morphine is a basically phenanthrene system, and you have a furan ring, then aromatic ring system here, methoxy, and then 2 carbon and this. And you ought to know this name. This is a very famous name in morphine chemistry. No, strychnine is indole. This is morphine. Morphine means as it can be viewed as a phenanthrene, it can be viewed as a isoquinoline. See, benzene, then this ring is isoquinoline. So, I mean actually morphine biosynthetically is produced from brucine also in indole alkaloid. This is thebaine. This is thebaine. Okay. If you now do this again, our the lithiation chemistry, butyl lithium, timeda, and TMS chloride. Which position would be lithiated? Okay. So, I will not write the full structure, I will write only the structure where the lithiation would take place. And so, you have a methoxy up here, you see there is no now aromatic nucleus, and you have a methoxy here. Methoxy is a well known ortho directing group in the metallation lithiation reaction. So, lithiation can take place here, right, lithiation can take place here. So, all these, then also you have a benzylic position here, actually lithiation takes place here. So, your the TMS is okay. Rest is same, rest is nothing, I mean no change, just basically this hydrogen, this indicated hydrogen is now substituted by this. It is quite difficult though. I mean I would have expected a lithiation here ortho to the methoxy or this one, but it is again you see here abstraction of the proton, the deprotonation is taking place. It is a sort of a benzylic position or ortho to the oxygen. But what next? This is L selectrite. L selectrite, you must know what it is. L selectrite would give you a rearranged product. I will write the rearranged product, you try to figure out the mechanism. Okay. In the next class, you try to figure out the mechanism. This OME, just elect a minute, TMS, this, then this is a ring expanded product and OME. Okay. You figure out the reaction, and L selectrite, anybody knows? It is a selective reducing agent, the name tells you, and L stands for lithium, and all the selectrites are boron hydrides, and that mean, I mean easy to remember, you just take trialkyl borane and lithium hydride together, that is basically the lithium. That means, in this case it is the secondary butyl, that means 3 of them, and then I said lithium hydride, that means hydrogen minus lithium plus. Why it is L selectrite? Because it selectively reduces the carbon carbon double bond. Like if you have alpha unsaturated system, you want to reduce the carbon carbon double bond, then this is the reagent,